Hello everybody. Part A, explain how to change to spherical coordinates in space using cartoons and formulas. Okay, so part A, a point P in R3 can be written with different coordinates corresponding to this picture. So I'll put my three axes of space. This is usually the x coordinate, this is the y coordinate, and this is the z coordinate. So this is my x, y, z space. And a typical point is somewhere in this space with an x and a y coordinate and also a z coordinate, like that. Okay? And now what we do is we first draw this triangle, which has a right angle. And what we notice is that we can also go over here. Okay. Now, if I call this phi, then I see that the height, the z-coordinate, may redraw it. This height, well, this phi, and this height here is this distance. So this hypotenuse is going to be called rho. It's a Greek letter, sort of like the radius. And now this is rho cos phi. Whereas this one is length rho sine phi. Okay? And then there's one more triangle that we'll need, and I'll do it in pink. This triangle. Down here, it has a right angle, and this angle I will call theta. And I redraw that triangle. And there's theta. And now what I notice is that this piece up here and this piece down here have the same length, and that length is rho sine phi. And what that means is that this length is, well, it's opposite the angle, so there'll be a sine theta. And then I put here, I'd usually put r for the hypotenuse length, the radius. But now I actually have a different thing that I put in place of r, because this is the hypotenuse of a right triangle. Finally, this piece over here is adjacent to theta, and so that's why it gets a cos theta. And again, we put the r, the replacement of r, in front of it. And this is trigonometry that we notice. Okay? And now, after having this, all this diagram, I finally say this gives us a map. A map. What is the map? It goes from rho theta phi space to xyz space, where now the x coordinate is here, which is this rho sine phi cos theta. The y coordinate is this length, and that's over here, theta. And the z coordinate is this length, which was over here. Okay. And this, this is a map from R3 to R3, where over here we have the, Over here we have the x, y, z space. And over here we have the rho, theta, phi space. And so that's why you might see x equals rho sine phi cos theta. Y equals rho sine phi sine theta. And z equals rho cos phi. Okay. And that, this map allows changes to spherical coordinates. That's what they call it. Okay, why do they call it spherical coordinates? Well, because if we just change the theta and phi, we move around on a sphere of radius rho. And then if we start changing rho, if we view it as an input and we can change it, then we start expanding and contracting our spheres. A big sphere out here versus a smaller sphere down over here. Okay, that's part A. Part B. Calculate the derivative of this change of coordinates map at an arbitrary point. So part B. First, the Jacobian. So here I have my map, is 3 by 3 because our inputs are three-dimensional and our outputs are three-dimensional. Its columns come from what? D by d rho. These are the three inputs, so that's what we have to take the derivative of. D by d theta and d by d phi. So let's do it. The Jacobian is, so first I have to differentiate with respect to rho. That's easy because the rest are constants, so that's all we have. Sine phi cos theta. Next is sine phi sine theta, derivative with respect to rho. And last is cos phi. That is the first column of the Jacobian. The second column comes from derivative on theta. Here we have cos theta, so it's a minus sine theta. And here we have sine theta, which makes it a cos theta. And here we have no theta, which makes it a 0. That's the second column. The third column now, differentiate with respect to phi. Here we have sine becomes cos. Here we have sine becomes cos. Here we have cos becomes minus sine. That is the third column of the Jacobian. But it asked us to calculate the derivative, and the derivative is a linear map. And it wanted us to do it at an arbitrary point. So we don't actually plug in numbers. So then, if this is the Jacobian, then the derivative is the linear map. Well, what is it? Well, our input space is three-dimensional, so our movement vectors, our linear movements, will need 3 coordinates. We usually call them v1, v2, v3 for the vector. You can, of course, call them anything you want. But now, we have to send it to this column, plus v2 times this column. So we're just taking a linear combination of the columns of the Jacobian matrix. And if we plugged in a point, this would be a number, a number, a number. But we didn't plug in a point. We're calculating this derivative at an arbitrary point to be specified later in an actual calculation. And the last column, the last vector that we linearly combine, looks like that. And this is the derivative. Well, I should say at rho theta phi. Okay. That's the end.